The next three experiments which I will describe involve the use of a furnace to heat the sample. This is the furnace in which the sample will be hung, and this furnace can go up to 300 degrees centigrade. The furnace is heated by a power supply, and if you apply a voltage to the coil and the furnace, then the temperature of the furnace will go up. For different experiments, we use different inserts which carry the sample with the connecting wires and the thermometer, and which can be hung from this support. I will now talk about calibration of a silicon diode and copper constantan coupled against a platinum resistance thermometer. Any property which varies with temperature can be used for thermometry. The pressure of a gas at constant volume, the resistance of a wire, the thermoelectric EMF generated when the junction between two dissimilar metals is heated, or the magnetic susceptibility of a material, or any of these properties can be used for thermometry. The resistance of a platinum wire varies almost linearly over a very wide temperature range. Platinum can be applied in high purity, so platinum resistance thermometers are used as secondary standards. In this experiment, we will measure the thermo EMF of a copper constantan thermocouple and the forward voltage against a silicon diode carrying a constant current as a function of temperature measured by the platinum resistance thermometer. All our inserts carry an aluminum block which is 1 centimeter by 1 centimeter in cross section, 5 centimeters in length. Aluminum has a very high thermal conductivity. We make holes in the aluminum block on the two sides, and we put a platinum thermometer in one hole for measuring temperature and the sample in the other hole. In this case, the copper constantan thermocouple is put in this hole. The silicon diode will be pasted on one face of the aluminum block, pasted on one face of the aluminum block with a layer of araldite. The connecting wires come to a circular terminal block carrying banana plugs. So this is the insert, and we have different inserts for different experiments. In this experiment, we have a 1N4148 diode pasted on one side of the aluminum block. Leads from the thermometer, copper constantan thermocouple and the silicon diode come to this circular terminal block. The aluminum block hangs inside the furnace. This is a DC power supply. This is connected to the terminals of the furnace to heat it. These two terminals, the two black terminals here, are the terminals of the silicon diode. If I connect a positive voltage to this terminal and a negative voltage to this terminal, a current will flow in the forward direction. So, I connect those two terminals to a constant current source. The positive terminal is connected to this and the negative terminal is connected to this, and I put the constant current source in the low current mode. The two switches are down and I adjust this pot to set a current of 2 milliamperes. The copper constantan thermocouples, they come to an RCA plug and they are connected to channel 1 of the differential amplifier. So, I switch on channel 1, thermo EMF will be read on this meter. I close the furnace with a small pad of cotton. If I don't do it, hot air will rise and go out, cold air will go in, so furnace temperature will rise very slowly. By blocking this hole with a wad of cotton, I am preventing convection current, so the temperature of the furnace will rise. I connect the power supply. I set a voltage about 7 to 8 volts, and then this is the temperature indicator connected to the platinum thermometers. It indicates temperature in degrees centigrade, and this temperature will start rising if you wait for some time. This is a multimeter which is connected to the two terminals of the silicon diode to measure the forward voltage. This forward voltage is 623 millivolts now, when the current is 2 milliamperes. The temperature here is started rising, and as the temperature rises, this voltage will come down and this indication will go up. We adjust the heater voltage so that this temperature rises 1 degree centigrade per minute, and every 5 degrees rise in temperature, we note the voltage across the silicon diode on this, and we note the thermocouple EMF on this. This we do for every 5 or 10 degree change in temperature. You can see silicon diode voltage has come down and this voltage has gone up. I will again repeat the arrangement. The furnace which is here is connected to a power supply. This is the aluminum block on which you have the samples. This is the circular terminal block. There are two terminals which are connected to the platinum thermometer on the aluminum block. They are connected to the temperature indicator. There are two terminals which are connected to the silicon diode. They are connected to the constant current source, and you set a current of 2 milliamperes. There is an RCA plug that is connected to channel 1 of the microvoltmeter. The voltage across the silicon diode is read on this multimeter set at 2000 millivolts. I take readings every 10 degrees. I note the reading, the voltage across the silicon diode, that is the first column. This is for a silicon diode. So, this is the temperature, this is the voltage across the silicon diode. I plot the forward voltage against the temperature, keeping the forward current constant. I used 2 milliamperes here. In my experiment, I used 1 milliampere. You find the forward voltage comes down linearly at the rate of 2.11 millivolt per degree centigrade. The intercept is 0.6574 volts. So, the equation to this line is 0.6574 minus 0.00211 into temperature. We can use this silicon diode to measure any temperature. We have to measure only the voltage, and from this equation we can get the temperature. How accurate will our temperature measurement be? For this, we use this equation, calculate the values of V at all these temperatures. The calculated values are slightly different from the measured values due to experimental error. This column gives you the difference between the calculated and measured value squared. This difference can be positive or negative, but when you square it, it will always be positive. You add all these error squares, you divide it by n minus 1, where n is total number of calibration points, that is n is 9, so you divide it by 8, that is the variance. You take the square root, that is the standard deviation. It is 0.9 millivolts. 2.1 millivolt corresponds to 1 degree. 0.9 millivolt will correspond to 0.45 degrees. So, if you measure temperature with this silicon diode, the error in temperature measurement will be plus or minus 0.45 degrees centigrade. This table gives the readings for the thermo EMF measured in millivolt. This is a graph where the thermo EMF is plotted against the temperature in degrees centigrade. This is fitted to a second degree polynomial. V is A plus B1t plus B2t square. The red line indicates the fit, and the parameters of the fit are given here, A, B1 and B2. From this equation, we calculate the value of V at all these temperatures. We take the difference between the calculated and measured value, square it and put it in this table. We add all the squares, divide it by n minus 1, where n is number of readings, that is n. We take the square root, this is the standard deviation. If you differentiate this equation with respect to temperature, that gives you B1 plus 2B2T. At any temperature, the value of B1 plus 2B2T is the change in the thermo EMF for 1 degree change in temperature. That will be about 40 microvolt per degree. The error here is 1.64 10 power minus 2 millivolt. So, you multiply it by 1000, it will be 16.4 microvolts. 40 microvolts is 1 degree, 16.4 microvolts will be 0.4 degrees. So, if you use this thermocouple to measure temperature, you will get the temperature to within plus minus 0.4 degrees centigrade.